Another day, another story. Several years ago, in a world of quantum mysteries and exotic concepts, a physicist found themselves in a place they least expected, a conference of string theorists. Our protagonist, however, hailed from the world of condensed matter physics, where they tinkered with materials like metals and superconductors, cooled to temperatures nearing absolute zero. String theory, on the other hand, explored the universe at energy levels far beyond anything conceivable in a laboratory. It delved into the enigmatic physics governing black holes and speculated about extra dimensions of space-time. Gravity was the focal point for string theorists, but for our protagonist, it was a mere afterthought. The gulf between these two worlds was not just scientific. It was cultural. String theorists were renowned for their mathematical prowess, while our physicists often found themselves bogged down in the dense equations and intricate concepts of string theory. The feeling of being a newcomer weighed heavily on their shoulders. Curiously, the gap went both ways. String theorists, despite their mathematical brilliance, struggled with some of the fundamental concepts of condensed matter physics. The author found themselves drawing explanatory diagrams usually reserved for teaching graduate students. So why was our protagonist there? In recent years, the condensed matter community had stumbled upon materials exhibiting quantum phases so bizarre that they defied conventional explanation. These materials entangled particles in ways reminiscent of the spooky action at a distance Einstein had famously pondered. Superconductors, in particular, were at the forefront of this intrigue. These materials, which carried electric current with zero resistance, had technological significance. Yet, understanding their properties and capabilities was a formidable challenge. Then, a glimmer of hope emerged. String theory offered an unexpected avenue to tackle these challenges. By seeking to unify particle physics and Einstein's theory of gravity, string theorists had uncovered dualities, hidden connections between vastly different realms of physics. These dualities allowed insights from one realm to be applied to another, translating entanglement problems into gravitational challenges. It was lateral thinking at its finest. But what were these quantum phases of matter that had captured the condensed matter physicists' attention? To understand, let's step back to high school physics, where we learned about solids, liquids, and gases. These phases are intuitive. Solids have a fixed shape, liquids take the shape of their container, and gases are easily compressible. Yet, the story doesn't end there. In a solid, electrons roam freely, creating electrical conductivity. This is the realm of conductors, insulators, and superconductors. Conductors let current flow easily, insulators resist it, and superconductors, a unique class of materials, allow current to flow without resistance. Superconductors, our protagonist's focus, exhibited extraordinary behavior. Electrons in them paired up despite their innate repulsion, forming pairs that acted as a single quantum entity. The theory of superconductivity, known as BCS theory, explained this phenomenon. These electron pairs, behaving as bosons, could condense into a state of minimal energy, allowing for zero-resistance current flow. But as the story goes, physics was turned upside down when high-temperature superconductors were discovered. These materials, like barium-iron arsenide, exhibited fascinating behavior. As more phosphorus was added, they transitioned from superconductors to something called a strange metal. Understanding this strange metal proved to be a significant challenge. The key lay in quantum entanglement, the phenomenon where particles' properties are correlated, even at vast distances. While entanglement might sound familiar, it had a twist. Unlike everyday objects, quantum particles like electrons didn't possess fixed properties until measured. The mystery lay in how these particles, once entangled, remained correlated even when separated. This was the spooky action at a distance that had troubled Einstein. Yet, experimental evidence confirmed this phenomenon, especially in materials like strange metals. Close to a quantum critical point, where materials transition between phases, electrons cease to behave as individual entities. Instead, they became entangled en masse, forming a vast network of interconnections. This network extended beyond our ability to directly describe, leading researchers to wonder if a theory for these quantum phases would ever be within reach. But then, they stumbled upon string theory. String theory, with its microscopic strings vibrating in higher dimensions, seemed worlds apart from the entangled electrons in condensed matter systems. However, the real magic lay in the concept of dualities within string theory. These dualities allowed researchers to transform intractable problems into manageable ones, providing a fresh perspective on complex quantum states. The extra-spatial dimension in string theory became a mirror for the entanglement network of particles in condensed matter systems. It was as though the spooky connections that troubled Einstein now made sense when viewed as distances through an extra-spatial dimension. Practical benefits emerged. String theory's mathematical solutions offered insights into the transition from superfluids to insulators, helping to explain the behavior of particles at the quantum critical point. However, challenges remained. The duality could simplify complex problems, leaving gaps in understanding the intricate details of entangled states. Thanks for watching. Comment and subscribe.